The Earth is a powerhouse of industry. Across the globe, 24/7, somewhere, somehow, someone is at work. Producing, making, distributing the products and services essential to our daily lives. But what marvels of manufacturing do everyday objects hold? Recycling, plasma TVs, fireworks, railway tracks, ink cartridges, 5 ordinary things, 5 extraordinary stories. Now revealed as we go behind the scenes, inside the machines to find out, how do they do it? Ever wondered what happens to old airplanes? They get recycled and get turned into circuit boards for use in phones, computers and TVs. So, how do they do it? Welcome to the Davis-Monthan Air Force Base near Tucson, Arizona. Davis-Monthan is a jet plane junkyard for the USAF. At Davis, you can find everything from F-4 Phantoms to B-52 bombers, all quietly broiling in the desert sun. This is where old planes come to die. But it's also where they get resurrected into something new. The Lockheed C-141 Starlifter is a troop and supply carrier that was once the pride of the Air Mobility Command. With over 40 years of service behind it, the Starlifter now faces a phased retirement program. But to salvage worker Ramon Martinez, the Starlifter is still a goldmine of reusable materials and components. Tons of metal sheeting, miles of wiring, thousands of electrical components. Martinez has already removed much of the plane's interior. All that remains is the shell. In one piece, it's too big for the scrapyard. But Martinez is about to fix that. With Martinez at the controls, a massive excavator comes to life. Such a machine is usually used in construction. But today, it's become a plane killer. Like a voracious beast, the cat advances on the Starlifter. What follows is not for the faint-hearted. First, Martinez rips off the pods that held the engines. Then he hacks off the wings, one by one. After that, the relentless jaws of the cat close upon the tail section. Finally comes the fatal blow. Like a predator tearing at its prey, the cat rips out the innards of the stricken Starlifter. It's not pretty. To some, it might even seem gruesome. But it's effective. In just 40 minutes, no section of the plane remains unscathed. What's left is not exactly bite-sized chunks, but it's small enough for transportation to the next phase of the recycling process. 1 kilometre away, the the Starlifter endures further destruction. It's a hot, noisy job, but it's nothing to what's coming next. They call it the Hammerhead Mill. It may seem like an old airplane's worst nightmare. It is in fact the heart and soul of the recycling process. First, the metal chunks are fed into a rolling mill. Steel spikes mash up the metal, and they do a good job. This is what's left. Thousands of small pieces on a conveyor. But now comes the tricky part. There are all kinds of materials here. Steel, aluminium, even plastic. Somehow it needs sorting through. And this is how they do it. At the end of the conveyor, a powerful magnet literally sucks iron and steel into a separate hopper, allowing aluminium and plastic to drop directly onto its own conveyor. A final manual check removes any pieces of plastic or unwanted items. And the recycling process is almost complete. It seems hard to believe that just 2 hours ago, this was a giant aircraft, abandoned, forlorn, surplus to requirements. Now this metal will soon be on its way to help make phones, computers, TVs, and a dozen other products, right across America. We live in an information-hungry age, and one of the most popular forms of media we use is television. But a revolution has happened that has changed television altogether. Not what's on it, but what's in it. Welcome the Plasma TV. Plasma televisions are filled with gases that allow them to be super thin. To build them means harnessing a fundamental cosmic force. The northern lights flicker in the upper reaches of the Earth's atmosphere. Lightning fills the sky with temperatures hotter than the surface of the sun. All the principles behind these natural wonders are harnessed to produce ultra-thin plasma TVs. The question is, how do they do it? It's a rainy day in Miyazaki in South Japan. In this factory, Hitachi turns out 500,000 plasma TVs every year. This may look like a normal television screen, but look closer and you will see not one, but 2 glass plates clamped together. It's what happens in between these glass plates that is the secret to the production of the ultra-thin plasma television. Between the plates lie a matrix of 1 million individual and minute cells, each one a fraction of an inch tall. Across the top and bottom layers of the glass are hundreds of thin electrodes, crisscrossing one another. Their job is to create an electric environment that charges a mix of inert gases that will soon fill up those cells. The gases are called neon and xenon. Once charged with electricity, they create plasma. You may have thought there were only 3 states of matter. However, after liquid, gas and solid, plasma is the 4th. It makes up nearly all the visible matter in our universe. By adding electricity to certain gases, you create plasma, which creates light. So how do you create the northern lights in a TV screen? First, fill it with the neon and xenon. This tiny glass tube is fitted to the back of the screen by a robotic welding device. Using the tube, air is sucked out, the gas mixture pumped in. With the tube now fitted, the panel is sent on its way to where the gases are waiting for it. 16 at a time, the panels enter this long chamber. In here, neon and xenon gases are pumped into the cells. The first step towards creating plasma. So, now the TVs are full of gas, but there's one major problem. Charged neon and xenon only generate ultraviolet light, something invisible to the human eye. The solution? A very clever bit of chemistry. Each cell has been coated alternately with a red, green and blue chemical, called a phosphor. And what this means is about to be revealed in the testing area. Soon, and for the very first time, electricity will pass through these cells. All the science and engineering has been building to this moment. This technician is creating an electric storm right in front of our eyes. Plasma is born. Each time these screens are turned on, electric current will charge the electrodes to create plasma. With a chemical reaction going on inside your TV, you want to make sure it's safe. So, they enter the aging room. In here, hundreds of screens are switched on and left on for hours to make sure the gases and technology are stable. The plasma screen is complete. But it isn't yet a TV set. There are no tuners, no receivers, no aerials. The plasma TV still has a long way to go. Generating sound and vision involves reels and reels of individual components being fired, one at a time, onto thousands of circuit boards. High-pressure plastic injection machines produce all the different front covers for the varying sizes of TVs made here. Then, everything is brought together on a production line. Circuit boards, which control the signal, the power, formats and tuners, are all placed on the inner back wall of the TV. But right now, the screen has a poor contrast ratio, giving off a kind of milky grey light. So, another screen is added to increase the contrast. Then, everything is checked. Colour bars make sure each TV is producing the correct colours, whites and blacks, rather than muddy greys. Test patterns, formats and functions all need to be assessed. These guys at least get to watch the front of a TV screen. Spare a thought for Satoshi Maruono. It may sound like robotic bedlam. However, to Satoshi's ears, all the chirps and squeaks are perfection. Until it sounds any different, of course. And some tests involve a highly technical process. He's listening for loose screws. Satoshi sees the backs of hundreds of TVs every day, but he'd much rather be watching the front.
I love TVs so much that I make them for a living. I don't have a plasma TV myself yet, but I do dream about getting one.
After packing and boxing, there is still a final check reserved for just 1 or 2 televisions. Every now and again, a television is taken off the line and has to enter the vibration chamber. A metal floor plate shakes up the TV to make sure everything is screwed together properly and that there are no loose parts. When you open your TV's packaging, everything should have been shaken but not stirred. As the workday comes to a close, the TV sets are loaded onto trucks to be shipped and sold around the world. It may be the end of this TV's manufacture, but it's not the end of the story for plasma. What started in the skies with the Northern Lights has found its way into space. Plasma gas is now used as a propellant in spacecraft thrusters. And back in the factory in Japan, the television sets quietly dream of the images they are about to show the world, as well as the countries they themselves are about to visit. Sunset over New York. It's July the 4th, one of the biggest dates in America's calendar. Independence Day. An air of expectancy hangs over the city. Only one kind of event can draw a crowd this big and this diverse. A firework display.
All over the world, people love fireworks. Nobody likes it more than the people in New York. We're convinced of that.
For days, a team from Macy's department store has coordinated a massive operation involving technicians, TV crews, police, and government and city officials.
We deal with so many city agencies and so many people that work for those agencies, outside vendors, volunteers. All told, there's about 5,000 people that need to come together and be on the same page for this.
All this effort has one purpose: to realize the vision of this man, firework designer Gary Souza.
For me, the first few aerial shells that go in the sky, I am just totally thrilled. To me, that's the best moment in the whole show, because then I know that things are going to work.
Souza knows he's only going to get one chance at getting this right. By definition, you cannot rehearse a fireworks show.
Basically, you get one shot at it, and if it doesn't work, it basically sucks.
The Macy's display promises to be special. Yet, no matter how awesome they become, all fireworks are based on a simple mix of chemicals and an even simpler technology. So, how do they get to be so spectacular? The story starts half a world away. In the Chinese city of Luoyang, they know all there is to know about fireworks. Because fireworks is what this town makes. Indeed, fireworks are so central to this city's way of life that they've even put up a statue to honor them. One of Luoyang's biggest employers is Black Cat. The company manufactures a diverse range of fireworks with exotic names and equally exotic effects. Making fireworks can be dangerous. To minimize the threat, buildings are spaced far apart and bunkers are set deep into an overlooking hillside. But there's one further risk, and it lies in the fireworks' main ingredient. This is black powder. It's a blend of charcoal, sulfur, and something called potassium nitrate. By themselves, each of these chemicals is harmless enough. But once mixed, they become highly volatile. Fireworks are designed to work at night, so Black Cat tests all its products under the cover of darkness. Black powder was first developed in China 2,000 years ago. Put a match to it, and it does this. The potassium nitrate in the mix acts as an oxidizer. When heated, it creates enough oxygen to make the powder burn. But the ancient Chinese alchemists soon discovered that black powder has a unique property. When it's packed into a confined space like a tube, hey presto. Pyrotechnicians call this effect the bursting charge. But the ancients also learned that if you make a hole in the bottom of a firecracker, you can direct the force of detonation downwards. You get what is now called a lifting charge. And that's what makes a firework fly. In the light of day, the manufacture continues. The simple rockets and firecrackers made here seem a million miles away from the spectacular effects we now take for granted. The cascades, the clusters, the rings, the starbursts. The secret to these lie in a heap of small pellets called pearls. In China, they make pearls from dried rice husks, coated with a slow-burning mix of powder and glue. To get multiple effects, pack the pearls into cardboard spheres called shells. To get different colours, add different kinds of mineral salts. Strontium for red, barium for green. To get sparkle, add flakes of aluminium. Link the shells to the main charge by time delay fuses, and lighting the rocket will set off an irreversible chain reaction. Each wave of shells ignited by the detonation of the previous wave. No matter how complex, all fireworks are based on this simple chain reaction effect. All you have to do is to make the shells bigger. July the 4th, Manhattan. As darkness falls, the crowds wait patiently for the big event. Back at the control center, the countdown begins. In a few short moments, the team here will unleash a barrage of high explosives on the city's skyline. And then, quite suddenly, it begins. An aerial palette lighting up the sky in vivid hues. At a rate of 1,000 shells a minute, the team launches 20,000 kilograms of high explosives into the sky. It's an awesome spectacle. To get a display that people can actually see, the fireworks are launched not in Manhattan itself, but from barges in the middle of the East River. The barges must hold a precise position against the East River's relentless current. If they drift out of place, they could end up firing shells over the audience. It's a nightmare scenario that haunts Macy's operations director, Bob Rutan.
I'm in constant communication during the show with the barges to say, okay, you've come 100 feet too close to the Manhattan side, you need to get 100 feet back towards Queens, or vice versa.
Fireworks bring out the kid in all of us. Even for Sousa's veteran team, this is a thrilling moment.
I love the fireworks the best. There's something magical about them. This was the event that caused me to want to do events for the rest of my life.
The result of simple chain reaction chemistry is a phenomenal range of spectacular effects. On July the 4th, thanks to Gary Sousa and his team, and a 2,000-year-old technology from China, New York City sees them all. It resembles a cathedral to industry. It feels like the gateway to hell. It's hot, grimy, noisy, and it's dedicated to making just one thing. Rail tracks. But these are no ordinary tracks. These are the longest railway tracks ever made. At 120 meters apiece, the tracks are designed to serve Europe's high-speed rail network. High-speed rail networks carry trains at phenomenal speeds, around 350 kilometers per hour. That's equivalent to a Formula One racing car on full throttle. Normal tracks cannot cope with the stresses and strains high-speed trains impose. Too many welded joints between sections of track. Too many sharp bends. To make the journey smooth and safe, you need fewer welds and gentler curves. And that means making single sections of track the length of a football field. So, how do they do it? The story starts here, deep in the heart of the Austrian Alps. The gingerbread houses and snow-capped mountains may seem a million miles away from heavy industry. But it's this spot that Austrian rail giant First Alpina has chosen to call home. The tracks begin life in a furnace. Steel ingots broiled to a searing temperature of 1400 degrees centigrade. At this temperature, impurities that float to the steel surface need to be cleaned off. But how do you clean a red-hot chunk of steel? As they emerge from the furnace, the fledgling tracks are about to face a violent baptism. Dousing in high-speed jets of water. The process is called descaling. The steel is so hot, the water literally explodes on contact. Descaling may be spectacular, but it's also practical. The explosive force has a scouring effect on the ingot surface. It's steam cleaning taken to the extreme. At this point, the cleaned ingots are featureless steel planks. Turning them into rail tracks requires some formidable hardware. In an adjacent workshop, you can see it taking shape. They're called rollers. Giant steel cylinders, carefully tooled with grooves that will mold the track head and stretch the steel to that final 120-meter length. On the floor of the plant, the giant tracks move back and forth through the rollers no less than 16 times. With one new red-hot ingot hitting the floor every 5 minutes, track rolling is a finely tuned choreography. And this is where the dance master sits. A control cabin looking straight down onto tons of red-hot steel. Get the timing wrong and you'd end up with the mother of all pileups. Tons of steel bent out of shape.
If you get out of step with the rail tracks, either moving through the system or coming back, then yes, a collision is possible.
To avoid pile-ups, the controller sends half-finished tracks up a giant off-ramp to allow the next track to enter the system. Once milled to the correct shape, tracks face another trial by fire. A giant circular saw cuts them to precise lengths according to customer specification. The tracks are now the right length and shape, but there's a problem. The track head is too soft. Soaking the cooling rail track in a kind of liquid plastic called polymer knits steel molecules together in a far denser pattern than that produced by cooling in the open air. The effect of head hardening is to reduce the contact between track and wheel.
The contact areas of steel wheels of a train in combination with the runaway with the head surface of a rail are very, very small. Only a couple of square millimeters per wheel.
The result, the wheels glide over the track head surface, and that means less friction, less wear. Back in the plant, the tracks get a final milling to make sure they're absolutely straight. And then comes the acid test. The tracks are long, they're straight, they're hard. But they're going to have to face 25 years of brutal use. So, are they safe? It's Praker Christian's job to find out. The machines that he looks after have one task: to spot the kind of imperfections in the steel that could cause a train wreck.
In the inspection area, we check the tracks for both surface and interior faults.
At a speed of 1.5 meters per second, each new track is fed through a series of different automatic inspections. Red and blue lights provide a visual scan for imperfections. Magnets check for surface deformation. An ultrasound array checks the track for interior deformations. The computer has spotted something, a suspicious blemish where no blemish should be. The slightest flaw in the composition of the steel could cause fractures or fatigue deep inside the track. If anything shows up, the track is diverted to a manual inspection area. The inspection must be thorough. Every scratch and blemish is closely examined. Sometimes it's only surface abrasion, but if it isn't, the track is rejected. The folks at First Alpina take track safety very seriously.
Passengers' lives depend on these rails, and that's why inspecting them is so important.
Once through the safety net, the tracks face a final hurdle: dispatch. In a lot of manufacturing, this is a fairly routine part of the operation. In the world of ultra-long rail tracks, however, dispatch becomes an epic story in itself. To get where they need to go, the tracks are themselves moved by rail. That means lifting them onto extra-long flatbed trucks. The slightest scratch or dent could send a 7-ton track back to the furnace. so the crew must maneuver each track on board the train without scratching it. So, how do they do it? With the aid of giant electromagnets, called cats. These robot-controlled hoists lift the tracks with breathtaking delicacy and daintily lower them onto a framework of cradles on board the rail wagons. The loading crew make sure the tracks are laid a couple of inches apart, close enough to make maximum use of storage space, but not close enough to touch. Padding and wedges make sure the next layer of tracks won't damage those lying beneath. The job is completed without mishap. Another consignment safely leaves the yard, destined for a location somewhere in Europe. You're looking at a modern miracle. It's invisible to the naked eye, yet so common it happens every day. This is a close-up view of a computer printer cartridge delivering ink to the page. These droplets occupy a tiny space, yet printer cartridges can fire millions of them a second in every colour, font and layout imaginable. So, how do they do it? Hewlett-Packard is the world's largest computer cartridge manufacturer. The company plant lies just south of the US city of Portland, Oregon. 800 people work here around the clock to supply cartridges for 20 million printers worldwide. Disassembled, the cartridge looks simple enough. It's made up of three main components: the ink, held in this reservoir, the firing chamber, and a small plate peppered with tiny nozzles. Together, as a microscope reveals, these components produce something amazing. Images and words delivered as a distinct series of tiny dots. Hundreds to the square inch, thousands to the page. To do such a job, the cartridge must exercise a very precise control over one thing: a droplet of ink so small it could sit on the tip of a human hair. Computer ink is a highly engineered liquid, 80% water, 20% a magic blend of solvents, pigments, and a kind of liquid plastic called polymer. The balance of ingredients is crucial. Here at the Ink Lab, technician Melinda Pride checks for colour bleed. It's called the egg yolk test. Put a blob of yellow ink into a dish, add a drop of black. The black should hold its shape, even when the dish is agitated. Ink is the cartridge's only moving part. It's pumped through tiny nozzles like these. Each cartridge has about 400 of them, set into a plate the size of a postage stamp. Like a micro machine gun, each nozzle pumps out 36,000 droplets a second. It happens so fast, it can only be measured in microseconds.
1 microsecond is a lifetime.
This is Mr. Bubble. His job, to boil tiny water droplets inside the cartridge firing chamber, so as to replicate ink velocity. At 2 microseconds, the ink moves in a flash.
To give you an example of how fast these things occur, a beam of light from this flashlight, when I flash the switch on, it goes 1,000 feet in 1 microsecond. So, If I aim it out the window, 1/millionth of a second after I turn the light on, the head end of that beam of light is 1,000 feet away from us.
So what triggers this rapid-fire capability? You're looking at a cosmic event. Inside the cartridge, an electrical resistor fires bursts of energy so intense they're 7 times hotter than the sun. The heat vaporizes the ink and pushes it through the nozzle. But relax, the thermal reaction is impossibly brief. Just 2/millionths of a second. Your computer is safe from meltdown. At this microscale, the slightest contamination could cause a cartridge engineer's worst nightmare: nozzle blockage. Here at the Droplet Break-Off Observation System, or DBOS, technician Geoffrey Langford reveals what a tiny speck of dust on the nozzle plate does to the ink flow. It isn't pretty. The ink gets blocked. The cartridge cannot fire. And that's why the ink is made here. They call it the clean room, a place completely devoid of everyday contamination. No dust, no dirt, not even a speck of dandruff. It's one of the cleanest environments on Earth.
This is a Class 10 clean room, which means that there are 10 particles in every cubic foot of air.
Besides ink, the clean room also handles fabrication of the nozzle plates and firing chambers upon which the cartridges depend. It's a high-tech micro-engineering operation, perhaps only rivaled by the space program. But when you're dressed like an astronaut, how do you recognize your fellow workers? For Jeremy Donaldson, it's a real issue.
After a couple years of walking up to someone and saying, "And you are," you start to pick up on the visual clues of the eyes and just the way someone's shaped and then how they carry themselves.
Back in the main plant, it's the end of the shift, but the cartridge must face one final hurdle. This man is a cartridge killer. His job? To get cartridges printing in the hottest, most humid environments imaginable. This is a climate-controlled test chamber. If it works here, it'll work anywhere.
We emulate different printing conditions. So this is a 35 Celsius with 20% humidity. So as an example, maybe printing in Phoenix, Arizona.
And when they're through baking the cartridges, they put them on a tower and drop them.
I drop things, and I enjoy dropping things. It's a great job.
So next time you hit print, think for a moment about the miracle of engineering going on under the hood of your computer's printer. And watch out for that thermal reaction. It's probably the closest any of us will ever get to a truly cosmic event. Through the endless cycle of days and nights, the Earth moves on. The world never sleeps. Somewhere, somehow, someone is at work. Producing, manufacturing, distributing. Since this program began, the world's factories have produced around 30,000 fireworks. Assembled 429 plasma televisions, forged 6 million tons of rail track, made 150,000 ink cartridges, and ground up 57,000 tons of metal for recycling. Even the most ordinary objects often have an extraordinary story to tell.